Good morning, everyone. Um, you have the last panel for this morning, and we stand in the way for your lunch, so we'll try to stay on time. This panel is focused on materials, and so I thought I'll give a quick overview of sort of just what we think when we think materials, and we've seen flavors of this keep coming up all through the workshop. But I also wanted to sort of highlight why when we think about materials and we're trying to think about modeling materials, whether it's actually physical modeling or through AI, we run into challenges, right? So I asked ChatGPT to make me a collage of materials, made pretty a boring one, so I said make it an interesting one, and then that's all it could do. I still didn't like it, so I went, searched, and found a better picture for material. So then I went and grabbed this picture. This is sort of the picture which came with the news of Google and quantum AI, quantum computing, right? So when you look at this picture, everything that you see here is essentially materials, right? From this chip that we're using, and we heard a lot about chip design and what it comprises, including sort of the material design for it, and we'll probably hear a little bit more in the panel. And then whether you're thinking of this light here, these wires here, or this packaging, right? This is a cardboard, this is probably a steel packaging. No matter what you're thinking about, including the clothes they're wearing, it's all materials. And we want to design all of these materials with different properties. I don't want my clothes to be as stiff as this material, right? And so that's kind of the aspect of materials that we're always trying to optimize for and trying to achieve. So if you look at a word cloud, okay, so again, I use ChatGPT for this, so you can see I have a lot of fun with ChatGPT. I said, create a word cloud of materials, and it did. And you can see it shows a very broad range of materials, from thinking about ceramics to alloys to superconductors, semiconductors, which we typically would call hard materials. They're like solid crystalline. But there's also lots of soft materials, which would be the squishy materials, like hydrogels, amorphous polymers, or some other bio-inspired crystals, biomaterials, et cetera, right? So they have a very broad variety of materials, but with that comes the challenge of properties, right? So now if I look at a word cloud of the number of properties these materials can have, and we want to try and optimize, it's even more crowded from everywhere, from getting its hardness, softness, thermal conductivity, glass transition, expansion, specific heat capacity, viscosity, et cetera. We want to be able to optimize for all of this. And it's so many properties that if you look closely, even ChatGPT got super confused. So you can see that this is actually not a word. It took a couple of properties and pasted over itself. It's kind of struggling here, kind of struggling here. It took it 3 tries to even get up to this, right? So it is that complicated a problem. And I like that ChatGPT allowed me to illustrate that. I'll give you another example, because in general, in this crowd, we've thought about what we refer to as hard materials. Let's think about another aspect of maybe soft materials, showing you sort of a refrigerator of all kinds of biologics. So these are basically drugs, except they're not powdered or solid. They're liquid formulations with something biology focused, and we'll hear about that in the next talk as well, right? So there's a protein or an antibody or a virus in there, such as for vaccinations, which we used to believe in. And if you zoom into it, this is essentially what it looks like. And this is essentially the kind of thing you saw when you went in to get your vaccination for COVID, right? And this has to be injectable. It has to be stable. And during COVID, we learned that you had to store them at really, really cold temperatures. And if you didn't do that, then you can't use it. And these vaccines are expensive, right? And this is true for lots of biologics. Because they can be unstable, you have to design what is called formulation. And you can think about it as a mixture of stuff that helps stabilize these. But what does that mixture look like? We don't actually know. In industry, they do a trial and error process. It's a very expensive process. Something works, we keep it. But even with that, we still need very many cold storage, right? Which is a big challenge. And so, of course, there's a lot of effort in trying to figure it out, but the challenge becomes the design space. I can have all kinds of sugar molecules, all kind of salts, all kind of various types of molecules which I can mix in different concentrations, and I could find maybe a formulation. So it's almost like saying, here is the spice rack, now try and find the best recipe, right? Which basically is an infinite search space. And so it's these kind of problems that we could probably solve through machine learning, but the challenge is that it includes a large scale of problems, right? So even if I take like the key ingredient, the biologic molecule that's involved, that I can break into many, many interactions and scales. So from very basic interactions, we all know oil separates from water. That's essentially what makes proteins fold, and this is why our body operates the way it operates. Two, more complicated, right? Then you can add some other types of interactions. You can add some structures. You can add a more complicated structure. This is what protein is, and this is essentially what AlphaFold and Rosetta Fold can predict, but they only predict the structure. But now a lot of these proteins come to form assemblies, and this is essentially the big working horse in your body, which both of those tools cannot do very well right now, right? And now all of this we've thought about just structure, but in reality what is important is not just the structure but the dynamics. So here I'm showing you sort of a virus capsid that's falling apart, and this is similar to your vaccines that we use, right? And understanding how it falls apart is a lot more important than just knowing the structure. That's the easy part. And so this is what it makes these kind of systems, these things of materials really hard, and this aspect of going from structure to property really difficult. Because we are doing a lot of physics. We heard about this in the last session as well. We are going many scales, but we also have to think about dynamics, both at the very small scales, the microscopic, nanoscopic scales, but also, again, we heard about this yesterday, or earlier this session, is when the process conditions change, your material will change, right? So we also need to account for those kind of things here, and this is at least my perspective of why I think doing materials modeling and then also incorporating AI into it has consistently been a challenge. And also is a land of opportunities. Okay, with that sort of introduction, I'll introduce the panel. So you've already heard from me. I'm an associate professor in the Department of Chemistry, and some of the protein stuff that I showed you is the kind of research that I do in my lab. That simply means that they agree with my philosophy. That's a sign from the superpowers. Okay. And I'm trained as a chemical engineer, so I think, but I do my research on the molecular side, so I like to think all the way from molecular to processes, and that's why this formulation design is one of the projects that we do in our lab, which I'm super excited about. But we basically try to study a lot of this on computers, so we do computer simulations of these systems. So those are the kind of materials we work with. And I also told the members of my panel that, answer these questions in your introduction, so I'll do it really quick, and then I'll pass it on to Arnab. The scale, I tend to look at the microscopic, nanoscopic scales, but I do collaborate a lot with my wet lab experiments, and really we try to ask. There's something about sound effects in me today, okay? First it was the screen, now it's the sound effect. At least you will all remember me, if not for anything else, right? And so we try and really bridge these scales and ask, how do we combine all these different data sources to really get to the objective that we want to get at? I think Gen AI has been really interesting and amazing in my field, and my field is very, very directly related to things that AlphaFold and Rosetta Fold did, so it was very exciting to see that. I will also go ahead and argue that the true Nobel Prize winners should have been the ones who thought about setting up and supporting PDB data bank. Without that, none of the other things would have been possible, right? But I do think one of the main limitations is this aspect of being able to capture the dynamics. That is still very limited. And in sort of our fields, we want to do the dynamics and the structure in context of the environment. And that is still, I think, a challenge for AI in general, but it's also a challenge to capture effectively in physical models. So it's no surprise that even AI struggles on that front. Okay, with that, Arnab.
Thank you so much.
Thank you.
Thank you so much for that wonderful introduction. And this word cloud is actually a great way to actually captured the complexity of the problem that we are looking at, but also it's such a combinatorial optimization problem that we are dealing with in materials, and that it's very easy to lose your way. And that's basically where I am coming from as well is, so by the way, my name is Arnab Bannerjee, and I am a faculty in the Department of Physics and Astronomy at Purdue University. And I consider myself an expert in applied quantum materials. And to give a little bit of my background, I had been working with a lot of quantum materials. My journey started with biomaterials and lipid-protein interactions, by the way. And then I went into quantum materials because I thought that this is one frontier we really need to solve, because we can't really keep on making quantum our enemy and to say that, look, we have quantum effects, and so we need to avoid it, as we do many a times I have been talking to my semiconductor friends. We really need to make it our friend, because then that actually opens a very new frontier. And that is where I think that AI is really going to help. And so what I started working on is a lot of semiconductor materials. I have been working on metal insulator transitions and how to make that better, and looking at the critical scaling laws, and to see where is quantum properties really expressed and where you still have a classical explanation of the problem. What is really quantum? What is really classical? And then I started working on a problem of something called quantum spin liquids, which basically is a very new state of matter. By the way, you can get several new states of matter when you get into quantum territory. Microsoft came up with one, by the way. And these new states of matters have certain very new properties which you cannot get in normal classical materials or in normal semiconductor materials. And I have been working on quite a few semiconductors doing actual experiments. I do neutron scattering experiments down to low temperature and high fields, transport experiments, both thermal transport and electrical transport down to low temperature and high fields. And I make some of these materials myself, both in the clean rooms of Purdue, but also I make some of them in my lab with the goal to understand that what could be a supply chain from kind of a cradle to grave that we can make with this material space. While at Purdue, so I was a postdoc at Oak Ridge National Lab working on neutron scattering and data analysis, and then I was a scientist there working both in neutron scattering, but also I had a joint appointment at the Quantum Computing Institute at Oak Ridge National Lab, which actually really helped us bring this problem that, okay, if we want to really harness the benefits of quantum materials, we really need to first understand the quantum materials. And the best way to understand a quantum materials is using a quantum computer, which was Feynman's original dream. Are we there? Or if we are not, why are we not there? And where do we start? And secondly, what can we use these quantum materials for? Can we make them new types of ultra-sensitive sensors, or new types of quantum memory, quantum computers, or new types of quantum communication channels that we can really make? And those are the problems that really faced us. And it was soon very apparent to us, and which is what I brought into Purdue when I became a faculty there, is that we need to create a quantum digital twin of the material. So we have the quantum material, and we get real data in quantum materials. And unless we have a quantum digital twin that resides in this AI space, cloud space, and in the computational space, then we cannot really predict what we are gonna do next. And that is where I think that we need a marriage of two techniques, one of them being quantum computing as it comes into maturity, and the other is, of course, AI. And I can probably talk later about what are the AI cases, but that's what my introduction is. Thank you.
Nathan?
So I'm Nathan Szymanski. I'm a postdoc here at University of Minnesota in the Chemical Engineering Department, and also an incoming assistant professor at UCLA in the Material Science Department. My work is primarily on, as far as types of materials go, bulk inorganic crystalline materials. So inorganic, typically these don't contain carbon. I look at a lot of oxides, phosphates, sulfates. Crystalline just means, you have some very small unit cell consisting of, say, 10 or 20 atoms bonded to each other in different ways, and these small unit cells repeat many, many times in all three dimensions to give you this periodic crystal. As far as how we look at these materials, I'm primarily a computational researcher, so we use quantum chemistry calculations, mostly density functional theory, some machine learning, to really try to look at the smallest of scales. So at the atomistic scale, how does the types of elements that are in your crystal and the way that they're arranged give rise to properties that we can actually observe macroscopically? And application-wise, we look at a lot of energy applications, so lithium-ion batteries, thinking about how we can design better cathodes, better electrolytes, to try and give you a battery that can get to higher energy density, better cycle lifetime, and so on. I would say generative AI has definitely been, picking up quite a bit in our area of these bulk crystalline materials. I would say like the past year, it seems like every week there's a new generative model with the goal of basically doing what we do, of materials design, but much faster. So the idea is you have some model, you say, hey, I want some material that satisfies these properties. Maybe it's a better battery cathode. And then it will suggest to you some crystal structure and some composition, which you then have to verify somehow, whether it's with more rigorous calculations or ideally with experiment. And there has been some success in these areas. There's a big Nature paper that came out, I think like last year, a few months ago, where they used Gen AI to propose these types of materials, and they did actually find that they could synthesize at least one of them. So you have one success. So that's showing you that the Gen AI for these bulk crystals is learning something and that it can generate a real material that you can then make. I think the biggest limitation, which we were asked about, is that yes, you can make it, but does it have the properties that you want for the application that you care about? So for example, in that paper, that Nature paper I mentioned, they looked at very simple properties like band gap and bulk modulus. These are things that are relatively cheap to compute, and because of that, there's lots and lots of training data out there that we can then feed into these Gen AI models. But in reality, if you're operating a battery, there's much, much more complicated properties that dictate the performance of that battery, such as the dynamics of the system over time, that there just really isn't enough training data out there for. And so I think that's where, in my opinion, the biggest limitation lies with these generative AI models for crystalline materials. So maybe we can discuss that a bit later on more.
Qizhi?
Thank you for the great introduction on the quantum material and molecular science. And I view this panel is about multi-scale material and how to bridge different scale together. So first of all, I'm Qizhi from civil engineering. So I consider myself a very conventional material modeler, although it's a very classical mechanics field compared to the next generation quantum computing is a little bit old day, but I'm assure you there is still a lot of unresolved problem in our field. And first of all, I would like to talk about a little bit about my research. My goal is try to develop the numerical methods such as finite elements method. Of course, in our group, we also try to do the hybrid strategy to combine machine learning AI into this numerical solver. But the goal is to predict the mechanics, the mechanical, thermal, and multi-scale response of a material in the large structure. In the larger structure, particular in extreme deformation that lead the material damage and failure. That's what I'm doing. So I will consider. In mathematical term, we call it a homogenization. We upscale the knowledge from the quantum mechanics or the molecular dynamic, but still, we know that there is a so-called emergent phenomenon. So once you put that material upscale to a real-world complexity and under complex environmental condition, new complexity emerge. So we still a lot of things to deal with there. In our group, we focus on heterogeneous porous media and composite. It seems a lot, but actually they share a common features. They have microstructures. And let me just introduce a little bit. Porous media is like a widely used to describe the geological materials such as soil or rock. And you can imagine there are some pore inside, so the fluid go inside. So you need to deal with the fluid. And if under some freezing condition, it expand, become ice, then you have the phase change. And also you deal with the fluid structure interaction, something like that. And composite is I mainly deal with composite in my PhD. I work on biological tissue, which consider the human muscle is like a reinforced composite. We have a strong material like a muscle fiber, and we have a soft material, extra cellular matrix. So we consider like that through the high fidelity stimulation, we can use that to investigate a lot of interesting phenomena like how human aging really affect the force generation, the force in our muscle. Why people age, then we lost our capacity of generate the force, something like that. So overall, we believe, understand this microstructure, for example, the arrangement of this microstructure or the morphology, and also the individual properties essential for predicting the upscale property of the material. So a key motivation for our work is to develop a digital twin. This is our long-term goal for this materials system, such that we can accommodate different applied condition. So we believe this can support like a forecasting of a natural hazard, understand how the geomaterial, how it behaves under different conditions, and also enhance even including the manufacturing, like the metallic manufacturing, you need to understand how really the phase change in the micro scale, but you cannot go in too deep scale due to the computational cost. So you need to sacrifice some accuracy, but live into certain level that you can do a high fidelity simulation while it's still feasible. And also design the resilient structure, which is back to my department critical need. So, speaking of digital twin, actually in our community, in the computational mechanics community, we have our first digital twin conference called Mechanics, Machine Learning for Physics and Mechanical Science in 2021 in San Diego. And actually next month in UT Austin, we have Artificial Intelligence and Digital Twin for Earth Science. So as you can see, the AI, this digital twin has been more and more popular in our engineering science domain. The second question is regarding the scale. So actually our engineering work on different scale as long as the so-called continuum assumption is still valid, which means the we assume the microscopic fluctuation must not cause significant variation in the average quantity. As long as this is satisfied, then we can work on. So from this mixed scale or meso scale problem to larger scale problem, we want to create a unified model how to simulate that. Okay, and so in our field, the generative AI is by far, based on what I know, is still primarily applied to generate realistic microstructure. For example, the rock sample, people will a lot of using on that. So there are some work from some of colleagues in Columbia and Rutgers University to generate some rock sample and use on the like a freezing, thermal freezing application. And also our group, I use generative AI technique for doing the constitutive modeling of the biological tissue. That is some of our work before. So recently, I want to mention there is one intrinsic limitation. I believe is about the thermodynamic consistency in our field, because our field usually work on so-called high consequence events. So the accuracy, not just the accuracy, the stability of the output from the model is more important than purely design, because we want to make sure the final outcome after long-term dynamic simulation, the result is reliable. Motivated by that, our group is mainly focused on how to strongly enforce the physics understanding in the machine learning pipeline. Or more specifically, we try to don't sacrifice too much accuracy that already well established in our field, like a finite element model. We want to strongly certify that, how to encode the AI back to our numerical solver, discretization solver. And in terms of the opportunity, I view the generative AI, there is one great potential is in handle the curse of dimensionality. So, and actually most of my work is based on that, how to reduce the dimension of a parameter space such that because it's naturally related to the Bayesian idea, so you can give a really physically realistic sample. Compared to PCA, we recently have a work compared to PCA and compared to the VAE, we realized the diffusion model actually is really give a much better accuracy. So we feel quite encouraged of that. And in the long term, the great limitation I just mentioned is about the nature of our field is a high consequence event. So I believe we need to understand better about the uncertainty that inherit from the model. So this is very important. Traditionally in finite element, we really care about the conversion. Why we care the conversion? Because we believe as you refine the model, you can get better accuracy toward the ground truth. But whether generative AI can provide this a property, when you increase the data, you really can train the model that make sure the accuracy is monotonically increased and the stability is still guaranteed under threshold. So this is some unknown. So I believe this is one thing our field really want to help to also push this aspect. And yeah, so I think that's what I would stop here. Thank you.
Right, thank you. I suspect you'll see the theme of it being physically aware, being physically consistent, being able to have uncertainty quantification, and then it actually being realistic, like Nathan mentioned, synthesizable, or like Qizhi mentioned, it should be stable, right? Will keep reoccurring whenever we think of materials and trying to design new materials. So we have a series of about 5 questions that I'd shared with the panelists sort of to give our thoughts on it, but now that we have maybe about 30 minutes remaining, I'm thinking we'll spend another 15, 20 minutes talking about those questions as much as we can, and then we'll open up the floor for any discussions. And we'll get through as many questions as we can. If we don't, it's fine, right? So this is I think it's almost like a trick question, right? The first question is, what are the typical design goals in your field of material science, such as multi-property, multi-fidelity optimization, constraint discovery, diverse batch generation, and how can GenAI approaches support them? So who wants to go first?
Okay, I will start. So I think that there is a whole flowchart in which the field has to work, which is that one has to make the material, which has touched upon that it has to be makeable, and then when we make the material, there is the purity issue and how does the properties change along with the purity, and it's a continuous variable. I mean, you can get different properties for different purities and phase transitions. There is and when you make this material, especially hard materials, we actually look at binary alloy phase diagram, and to look at the electronic properties, we have to look at the DFT. So all of that kind of inputs into what is really makeable, and when you make it, what is the band structure that you have. And that is already a tough problem. As you know, that there is a lot of DFT AI tools which are being discussed right now, which are coming up. And then there is exactly what is synthesizable is, and at what temperature would you cook the material? And when you cook the material, exactly what is the band gap that you get, whether that's a direct or an indirect band gap, and can AI help there? But then there is this AI for data analysis, and for example, I deal with neutron and X-ray data, and neutron data, when you take the data set, you get like terabytes of data at a time. And it takes a graduate student, or even me, 6 months to basically figure out, okay, which is coming from phonons, what is coming from magnons, what is coming from spinons, what is a quantum effect, what is coming from single ions, what is coming from multi-ion effects. And that is one space where I don't think that if we can train an AI model to figure out where to look at such data, it would be extracted much quicker. And that's, there is a little bit of effort going on in that effect at Oak Ridge National Lab with the Summit supercomputer, where there is a group which is already trying to look at some of these. And then there is this huge problem of parameter estimation. And parameter estimation, it comes by different names. So we call it Hamiltonian discovery, which is that if you have a data, what is the Hamiltonian it corresponds to? And it's a really tough problem. But that's the bottleneck, because once you know the Hamiltonian, you know how to change things, whether you need to add defects, whether you need to put strain, whether you need to put another material on top of it. That problem becomes easier. But Hamiltonian estimation, and Hamiltonian, by the way, in the computer science, you might call the Hamiltonian an objective function, so which is basically the lowest energy ground state that you can get in the material. And to do it classically is one thing, but to do it quantum mechanically is a QM, a hard problem, is what we call, and which means that in order to find the Hamiltonian, and I have been working with several companies, I mean with IBM, with Continuum, Honeywell, with D-Wave, and that is the same problem that comes up over and over again, is that how do we solve this problem? And one of the ways in which people have been thinking, and especially NVIDIA, with whom I think we will go through into an NDA very soon, is to see if we can use tensor network methods and get a gate-based description from tensor network methods to create a set of gates which we can say that that's a very good objective function to start with, and then move from there. And then there are other AWS is also very interested in it, from what I know. And once you go through a parameter estimation, then it is the property discovery part. So if you know the Hamiltonian, let's say, or if you have some idea, what are the properties that you can get from certain Hamiltonians, that will tell us how to tune the system. And device design comes right there. So what type of devices you can design. And so what we find is that there is AI in every space. I have already worked in AI a little bit to, for example, to look at the neutron data analysis. In fact, we had a material called dysprosium titanate and RuCl3, ruthenium chloride, and we got these huge neutron data sets, and we actually trained a machine learning algorithm to figure out what the Hamiltonian parameters could be. It's difficult because we were using a semi-classical model, which only is approximate, but we can also do a quantum model, and then doing the quantum model is the holy grail, but it's also the most difficult one, where I think that quantum computers maybe someday would help. But at the same time, I mean, in the quantum computer, to look at the properties, you have to do something called time series evolution. Quantum computers are great in time series evolution because it's a Schrodinger's equation which is working there through trotterization. But we have noise. Then how to cut the noise, how to cut the effect of the noise to look at the property that you really want to see. So those are all the problems that comes together, and where I think that we can really take the help of AI. Thanks.
Yeah, so my thoughts are generally pretty similar to Arnab, so I won't repeat too much. But he brought up a great point at first, which is stability. So, as computational researchers trying to design new materials or use Gen AI to propose new materials, thermodynamic stability is usually like the first filter we impose, because something that is stable or close to stable is much more likely to be synthesizable than something that is not. And I would say to contextualize this in the current generative models that are out there, typically they report stability rates on their proposed materials around like 10% or so, which depending who you ask might be great, might be bad. It sounds like a low number, but if every 1 in 10 material that you're proposing is something you can make and is actually great for your application, then maybe that's not too bad. But that brings us to the next point, which is, okay, now we need it to have the properties that we want. And I would sort of subdivide this into 2 categories, which is, one, the properties of your material in its nice, pristine form, basically the form that you've modeled it as an approximation, assuming that it's this nice, perfect crystal. And that gives you, a reasonable starting point to try and filter the good materials from the bad materials. And again, GenAI, I think, does actually pretty well there. There's been a lot of work out there that have trained these GenAI models on sort of these simple idealized properties. But then there's level 2, which is, okay, once my material is containing lots of defects, lots of impurities, vacancies, inclusions, whatever else, that's going to have a really big impact on the properties that you care about typically. But these are things that still to this point generative AI doesn't really account for, just because they are so much more expensive to model, and generally there just isn't enough training data to feed into these Gen AI models. So again, I would say that's probably the point to focus on moving forward.
Thank you. As mentioned by the previous speakers, so I think it's very general requirement, because in our field is quite engineering or customer specific object. Based on for our targets built in natural environment, of course, the safety, resilience, and sustainability is always a general requirement. But different specific domain scientists have their own idea. For example, I learned from one of my colleagues in transportation. They point out that for pavement material, compaction ratio is really key property seeking by the MINDA, Minnesota Department of Transportation, because it really relates to the porosity level and how resilient the pavement can last, especially given the extreme weather in Minnesota. However, for the steel, for the concrete, that of course always is the material strength. How much can you resilient to the high load and the impact? Fracture toughness is also an important consideration. So I would like to generate, but from a point of view, so actually I'm quite interested in the idea. I mentioned by which speaker is about the foundation model of the material. I really see this, if it is successful, that will mean a lot, because we deal with so many different materials in our daily life, in our engineering. If we really can have a model that can majority to handle different characteristics of a material and can utilize in our design and optimization, that will be saved a lot of effort. So speaking of that, there is another level of design in our field, is more like a structural material design, which means we not only design the components of the material, we design the structure, the microstructure of the material. Is like related to the so-called topology optimization in our field. Actually, I'm working with faculty Qizhi in CS department to try to develop a more general constraint optimization framework can apply to this our structure material design. So I believe this is also interesting directions. Thank you.
Wonderful. Actually, speaking of microstructures, I know Qizhi gave the example of concrete, but it's also very much relevant if one thinks about biomedicine and thinks about designing drug delivery materials, right? Something that you can put in your body which would carry the drug to, let's say, your brain. to a brain tumor, sorry, right? And so in that case, you want the structure of the material to be such that it can absorb the drug molecules, but it's still as flexible enough that it can penetrate through your brain, or it can be injected to the location, but still delicate enough that once it's done its job, it can disintegrate easily and your body can remove it without it getting toxic. So there is not just, in all of these cases too, it's designing the microstructure stuff, but also aging, which I think is typically is harder because, again, their data is scarce. So even getting those aspects of materials is challenging. Okay. The second question that we had was, what are the most promising near-term and long-term discoveries in material science that could be enabled by Gen AI, analogous to breakthroughs like AlphaFold and RosettaFold in the life sciences? And as the lead of the panel discussion, I'll just jump in and say this because I've been very close to this discussion about AlphaFold, RosettaFold, and its limitations and its benefits too. I think AlphaFold and RosettaFold really put us into this, I think, like momentum of trying to really use AI to solve a lot of protein-related, biology-related problems. And one place where it just has gone, I want to use the word bonkers here, is in trying to do the discovery of drug molecules, right? Small molecules that you can use as medicines, that you can use for treatments of various diseases. And the reason why it can work is now because we have this collection of lots of protein structures. We know where they come from. We kind of know how they function. And so now we could try to use this whole aspect of AI and generative AI to find those new chemical molecules that might actually function better. And I think this is a really interesting and very cool near-term success that can happen, but one of the challenges or I think two challenges that have emerged, both of these tools or such structure prediction tools can predict the structure, but again, as I mentioned, it's not guaranteed that they will actually synthesize in the lab. And in fact, there are studies where, AlphaFold predicted, let's say, 100 structures of different sequences, and when they went into the lab, not a single one folded into an actually functioning protein, right? So that challenge is still there, which basically means that we still need to capture some aspect of the physics to actually say, oh, well, is that structure even possible or not? And the second thing comes back to the dynamics, the time series. The fluctuations are super important at these scales, and they really make a difference in terms of whether your protein will function or not, because without those structural fluctuations, it may not. It's not a rigid body, so it's not going to function if it doesn't have those dynamics involved. And those dynamics change with the environment. And so being able to capture all of this in sort of any model, especially in Gen AI, would, I think, be the next big step. And there are lots of companies, including Microsoft and stuff, that are trying to do that, but the challenge becomes having enough data, especially because we are trying to span a very high dimensional space of just the design itself. And so they have some models, but again, there's no guarantee that they work. But I think that's kind of the direction, at least from life sciences, biology perspective.
I'll be short on this one, but you have touched upon a very important point, which is modeling the fluctuations and understanding what are the various steps that are involved in the fluctuations, which site will bend, which site bends, and that has what effect on the other sites. And it's a problem which has a multivariate and a multidimensional character. And in fact, speaking for AI for quantum, I think that this role of fluctuations is also something which is being increasingly discussed as something that we need to understand using AI. In fact, there is a theme right now which is train the AI on the quantum data as long as you have the quantum coherence in this quantum chips, so that you can understand what would happen in the long time scale when the quantum chips have actually lost their coherence, because as you know, that coherence and noise is still a problem. And that actually helps us understand very minute fluctuations, very small scale fluctuation. Like if you know what is, let's say, a very high energy phonon mode in a material that gives you some properties, what is the lowest energy mode doing Phonons are, by the way, certain types of particles which help to carry vibrations and sound energy. But they're both fast and slow of them. The fast are probably accessible, but how do we get to the slower ones? So those are problems where AI is being trained with the quantum data. But at the same time, I think that the role of AI is definitely from process design, and the dream that I have, for example, is to take it all the way from crucibles to chips. What is the process that where AI can really help? And what we are really talking about is designing materials out of the ideal conditions, getting to the ideal material which satisfies that particular objective function that we really want. That's expensive. We can make a material, we always try in a lab, we try to make A and we get B. And that's pretty normal. But what I think AI is going to help is that what is B useful for? And what are already the good things that we have in B, and to what extent the properties that we want in A are already expressed in B and can be useful for other things, given that certain properties that you can already exist that you can have trained the AI model for. So that's where I think the victory really lies.
Okay, in the interest of time, we'll move to the next question, but we'll let Nathan and Qizhi answer that because Arnab and I have spoken too much. Go ahead. So the third question is, how should we evaluate Gen AI systems in material science? What evaluation strategies align with scientific end goals?
Yeah, so I think, up until this point, we've talked a lot about stability, synthesizability, having the properties that we want. So in terms of evaluating your generative AI, of course, the obvious metrics to look at are what percentage of materials or molecules that you're generating are something that's stable, that could be made in the lab, and how close are their properties to the properties that you designed for. I think one other metric that we should really think about during evaluation is also novelty, or sort of the degree of novelty. We've done a lot of benchmarking in our group on these generative AI models to propose new materials, and what we find is that there's generally a very, very strong trade-off between the stability rate and the novelty rate. So, okay, maybe you can generate a lot of materials that are realistic, they're stable, but they basically match something that's been discovered for the past 8 decades. Or maybe it's not an exact match, but you took a material and you swapped out one atom out of 20 atoms in the unit cell. And most people would look at that and say, well, that's kind of a trivial change. Would you really consider that to be novel? And so I think as we evaluate these Gen AI models, we want to kind of strike the right balance between generating some really new material, something outside the box that a manual human researcher would have never really thought of, while still being something that is realistic and could actually be made in the lab.
Answer the same question?
Yep.
Okay. Let me double check. So for this one, I believe I'm not the expert for that. I'm kind of just a user of this AI. So currently, in practice, what I do is I will check some similarity matrix. I just, the generative output compared to the ground truth. I usually will have some high fidelity simulation data, and also will have some collaborator from experiment to provide some sample. But I would like to mention one thing is that because Optimate, my goal is to do the inverse modeling or that kind of put this generative AI in the loop of a solver. So which usually allow me can generate some physics-based another level of output. So I will particularly check the physical consistency through this loop. So so I think I will more focus on the physical consistency, because as you know, generative AI maybe is good to directly produce the first level output directly for comparison, but what is the derivative of this output data? Then this is something is less controllable. So, but we will be really interested in looking at this kind of a matrix, which is important in mechanics or physics.
Yes, actually, please do.
Uh, just to take for this, I might not believe it and it might be naive, but it seems like there are lots of things that AI could do for sciences. But it also seems to me, just for a devil's advocate point, that, like Nathan, you mentioned that we ran Gen AI for a property with it was a simulated property, which it showed good results. But then I went to a lab or some other property and saw that it did not do well. I think this panel is perfect in this sense. There is a physics person, a computational person,
Chemistry.
a machine learning person, like physics simulations, and a final experimentalist. So it seems to me right now what we're doing is we are doing Gen AI on one property, filter the results, then go and check on the other one. It seems to me all of these should be in one loop somehow. So I think thinking about how all of you can work together is probably even more better for AI, I guess.
We certainly need a consortium here, right? That's what we are really defining. But I think that you bring a very important point, which is benchmarking. I think that what are the right benchmark questions and benchmark checkpoints that we should have to say that, look, we have benchmarked it enough that we know that the AI model works, either for synthesis or for looking at the parameter estimation or whichever problem, but at the same time, we should not be training it so well that it just misses what we have not given it. And especially we worry about that in physics, because there is always new physics which is remaining to be discovered, which is, I think that there has to be a loop which needs to be set up, a feedback loop, and the questions there would be, do we actually make another material, or do we actually tune the material in a way which AI informs us and see whether that really worked?
Yeah, I will say that it's also possible. I think one of the very amazing opportunity that AI gives is the ability to bridge these different scales and different properties and approaches, because typically that's been the hardest thing to do sort of in physical modeling. So just again, drawing from the work we do, the two experimental groups that we work with, one of them is a protein person and one is a virus person, and they actually put a real virus in with all the different formulations and check the infectivity. In our simulations, we will never be able to do that kind of simulation. The ones I showed, the pretty movie I showed, is one of the most expensive you can do at this stage, right? But what we can ask is, what can I learn from my molecular simulations that correlates with what they see in more real systems that then I can use as a filter in high throughput screening? And that bridge, I think, comes through AI because it's a complex function. It's very hard. And generally in bio, but I think this is true in materials, it's also a very fine balance of interaction. So there are too many knobs, and there's a lot of correlation. And I think AI there can do a really good job of identifying that and helping us sort of create that complex function. And that's essentially kind of the direction we've been trying to take. Right,
I have.
Yes. Okay.
I got it.
Sorry, we'll do this question, then we'll
you could have
come.
continued. So I think the title says, what the Gen AI can do for science. I would put the other way, what science can do for Gen AI. Because coming from where I am, if you take chemical engineering, there are two things that are important: combining molecules, catalyst; separating molecules, membranes. And if you take batteries, the same thing. You take nuclear engineering, all of that, we are looking at the other way around. What are the things that we need without any application? Just material discovery is good, but without any application, you're just discovering stuff. But there's two things. One, even if you discover it, you don't know how to scale it up. Can you actually manufacture it? And in fact, battery manufacturing, the biggest problem is the supply chain. Okay, when you take the cathode, anode, and graphite and all that, you need the supply chain in terms of scaling up the production. So my question would be the other way around. What are the applications that you're looking for, and that might drive what Gen AI can do or cannot do, actually. Okay? So the feedback coming from this to Gen AI to say, like, here are your limitations, and if you want to do what we want to do, and what can you improve? So we always think that Gen AI can solve science problems. It's the other way around, actually. So that's what we are looking at the DOE, so looking at what is that to use. Gen AI is a tool.
Right.
Okay? AI is a tool. It cannot be this way, it should be the other way. So,
Right. Actually, I was reading an article recently and I really liked what they said. They said it's not Gen AI for science, it's Gen AI and science. And I think they go synergistically, and it's, like you said, it's a tool. And everything in science that we have access to is a tool, and we can use all of them synergistically. But I'll also let others answer.
I definitely agree. I mean, like you said about battery manufacturing, I know in especially computational research, a lot of times you'll propose some, supposedly excellent new cathode material with the right performance, but it relies on some weird chemistry or some weird precursors where the supply chain is just not readily available. And I know there has been some work done on sort of the forward ML to try and incorporate these metrics into the predictions so that you're only recommending materials or chemistries that could be manufactured at scale. I haven't really seen much on the generative AI side to do that, but I agree. I think it'd be a great idea to actually feed that data into these models so they're only proposing things that are reasonable.
I have a quick question following up on Qizhi's comment that you want to check the consistency of the physics, and I think that's a wonderful idea. However, what happens when your physics, so there's also unknown relationship in the physics that we're not so sure about, right? So in that context, how can you do the physical consistency check, right? So that's a question for Qizhi. The question for Nathan is, do you have some important insights about how to ensure that you get a diversity of the outputs from the Gen AI so that you get something that's not really seen in the examples, right?
Okay, let me take the first question. Thank you. I think this is very the core question. I always think about this question. Actually, from my point of view, although we always speak of physics, it seems physics is like a ground truth and already there accessible, but actually from my point of view, it's not true. Physics also have its resolution. Physics also has its uncertainty. Actually, if you look at the history of science from Aristotle, we based on the empirical observation to advance the theory gradually. So this is a good point. And in terms of practice, even when we talk about a well-defined partial differential governing equation there, which discretization method you use that to imply in AI actually will cause difference, will cause the performance difference, whether using strong form or weak form, the groundwater equation, it causes difference. So, but this is a less study area. So I fully agree. So of course, in terms of handles the problem, I see a lot of methods. For example, people using emulator, try to using a neurosymbolic idea. But if we look at the essence of this method is actually based on approximation theory. You still need a model. So it's still based on some kind of understanding. But as I want to ask the question in my introduction is that I always believe how to properly evaluate this general AI input in terms of accuracy, conversion, and stability is still the long-term goal that we all need to really figure out. Okay.
Yeah, so your question was on how do we ensure diversity and novelty in the outputs that these models are giving us, which I think is a really great question. I think there's maybe sort of like a smart way and a dumb way to do it. Both are kind of equally valid. I think the smart way is that these models typically have some sort of latent space representation of the materials. So let's say you're working with an autoencoder, then you have some low-dimensional vector representation of this crystalline structure. And based on that, we can inherently measure distances between materials that are being generated. And so basically, What some models will give you is some hyperparameter that controls where exactly in this latent space are you sampling, and are you sampling sufficiently distinct regions of it to generate materials that end up being very different. But then those also end up usually having a much lower stability rate, so it's a trade-off. Maybe the simpler way is to just basically generate materials with these models, and then just reference whatever's being generated against every known database you have of materials that have already been reported, and have some way of measuring how different these materials are from what's already known. And then if you're generating a bunch of stuff that's already known, just keep generating, right? I mean, with these Gen AI models, they're not slow, right? They're usually very fast to generate a new material. So it really costs you very little to just keep generating new stuff until you find something that, in your mind, is sufficiently different.
It's made of speculation around here. So in 2013, the Nobel Prize in Chemistry was given for the development of multi-scale models for complex chemical systems. It's chemistry. In 2024, we got it for computational protein design, which you just mentioned, AlphaFold. But AlphaFold never explained the science behind why it did it. So any speculation what the 2035 Nobel Prize in Chemistry will be? Every 10 years.
That's a good food for thought.
Also, it will be for the chemistry that leads to new types of, I would say, I want to say the chemistry that leads to new kinds of quantum properties such as quasi-particles, which will completely revolutionize how we look at energy transfer, for example.
No, I'm not a chemistry science, but I just want to point out I work in DOE labs before, and I work on one project related to flow battery, so also using AI to help to do the inverse modeling, and also I work with hydrology using just AI for subsurface science. Then I can tell, depends on the level of physics, the established physics, people have different perspective on AI. Clearly, the chemistry people actually like AI a lot, using graph neural network too. But so my understanding is like if the physics is less understood in the field, actually AI will advance rapidly.
I think it's also a little bit related to how quickly you can generate training data. And I think, at least in chemistry, and correct me if I'm wrong, I feel like DFT has done a good job generating a lot of data because there were databases for crystal structures, etc. In sort of getting it a little bit higher to like soft materials, it became even more challenging because now you have to really account for dynamics. You are at a high temperature range where things move around. And you need to be able to capture that. And I think so there we don't have as much data that we can put together and like fit stuff to. So I think that's kind of where it's been a little bit more challenging, I think, AI. But I will say that, you know, if you're thinking about, at least when I'm thinking about future of AI, I would say an exciting advance for me would be where we can actually realize this dream of we want to find new things at the molecular level, whether they're new materials or new formulations or new sort of constructs, because in proteins and enzymes, you're not finding new necessarily enzymes that are too different. You're finding enzyme that maybe will do something different than what they've been made to do already, right? So that's a different form of diversity. But you can do that to then say, this is the way you go and realize this in reality, right? That would be really what we are all after. And I think approaches that will allow us to do that would be the biggest advance in my mind. All right, with that, I've been told to stop talking and let you go have food. Thank you.